and I work on GIS and remote sensing. So often this means I work with our customers to answer technical questions as they're working in Lens on remote sensing. And I also work with some of our data providers. So big picture, what I'm hoping to cover today is whether you're brand new to remote sensing or have some experience, I'm hoping to give everyone sort of a foundation of knowledge on remote sensing, and hopefully you'll get some additional sort of tips for interpreting imagery or some better understanding of different types of remote sensing data. So more specifically, what that'll look like is I'll do just a quick definition of what actually is remote sensing, then lay some foundational knowledge going over the electromagnetic spectrum. And then we'll jump into specific types of remote sensing imagery, first talking about true color, talking about some tips for interpreting imagery and considerations for selecting imagery. And then lastly, we'll talk about false color imagery and index layers. And like Em said, feel free to drop questions in the chat as we go. I'll try and monitor as I go along, but if I miss any, don't worry, at the end, we'll have plenty of time for questions as well. So first, just jumping right in, what is remote sensing? So technically, remote sensing has a pretty broad definition, really encompassing anytime we are sensing or measuring and gaining information about something from a distance. So under this really broad definition, cameras and even our eyes count as remote sensing. I'm sitting here, I'm looking at my computer screen from a distance, and I'm gaining information. But usually when we talk about remote sensing, we mean something a little more specific in practice. And what we're usually referring to is satellite or aerial imagery or measurements of the Earth's surface to gain information about things going on the Earth. And there's a bunch of different applications of remote sensing, from real estate to insurance to meteorology. Today, I'm mostly going to be focusing my examples on the environmental applications of remote sensing. So we're going to get a little bit technical here for a minute, talking about the electromagnetic spectrum, but hopefully this will give everyone some additional foundational knowledge to better understand some of these different types of data that we'll talk about later. So the electromagnetic spectrum, you might remember this from high school physics, or maybe not. This is just a spectrum of electromagnetic radiation, which is essentially just a specific type of energy that travels in wavelengths. And we can see here that visible light is a really small portion of this spectrum. And this is the type of electromagnetic radiation that our eyes can see. Of course, there's a ton of other electromagnetic radiation that our eyes can't see, and some remote sensing devices enable us to get information outside of the visible light part of the spectrum, specifically most often in the infrared portion. A pretty fundamental idea underpinning remote sensing and even how we interpret what we see with our eyes is that different objects will absorb and reflect different wavelengths, different parts of the electromagnetic spectrum in different amounts. So if we think about just visible light for a second, as an example here, clouds, for instance, usually appear white to our eyes, and that is because they are reflecting all of the wavelengths of visible light. So all of that light is being bounced off of the clouds, very little of it is being absorbed, and that's why it looks white to us. Similarly, with vegetation, it has the highest reflectance in the green area of the wavelengths and absorbs more other wavelengths more. So that's why it appears green to us, because it has the highest reflectance in the green area of the electromagnetic spectrum. So this idea can be extrapolated a little bit to the concept of spectral signatures. So this graph here, what we're looking at is a portion of that electromagnetic spectrum, just from visible light to including the infrared. And we can see that different objects like water, vegetation, and soil will reflect different parts of the spectrum in varying amounts. We can also see sort of some of the value we get by looking in the infrared space, where even vegetation and water might be reflecting similar amounts in the visible spectrum. There's not a huge difference here, but as soon as we get to near infrared, water basically absorbs all near infrared, doesn't reflect it at all, whereas healthy vegetation has high reflectance there. So we're getting a much greater difference in those values, which can help us then, if we have a near infrared band from an image, we can more easily and quickly identify the difference because we have that wider gulf to differentiate water from vegetation. So this concept, these spectral signatures, are pretty foundational, and they really underpin people who develop different indices in remote sensing to help us specifically look at vegetation, for instance, or there are even people who will get the spectral signature for a specific species of a plant, and that spectral signature will then help them be able to make bespoke layers, for instance, because they know, okay, this plant should have specifically this value of reflectance at this part of the electromagnetic spectrum. So we're not going to really be talking about specific species, but this is sort of where you can get really in the weeds and in depth with remote sensing, talking about these spectral signatures. And one other note on the electromagnetic spectrum is that different sensors for remote sensing will capture different portions of that electromagnetic spectrum, and they can capture those different portions, or bands, as we often call them, at different resolutions. So this is a good example, just thinking about visible light. If we have black and white film, also called panchromatic film, that will be just one band across the entire visible light portion of the spectrum. So kind of low spectral resolution, it's just capturing one band for all visible light. Whereas multispectral, or color, will capture visible light in 3 bands. So that's higher spectral resolution. We even have, coming up in remote sensing, there's also now hyperspectral, which would have, tens of different really thin bands capturing within visible light, and of course also outside of visible light as well. And then I just want to make one note here about colors. I found this confusing when I first came to remote sensing, is why are we talking about blue, green, and red instead of blue, yellow, and red? I thought yellow was a primary color from art class, but it turns out that mixing paints works pretty differently than mixing light. So our computer screens work this way by displaying varying amounts of red, green, and blue light. And that is how all the images we're looking at are displayed. So for mixing light, red, green, and blue are actually our primary colors. And you can see here, when we mix those, red and green give us yellow, and all 3 will give us white. All right, so moving on to some types of imagery. First off, we have true color imagery. So this is true color, meaning the colors look true to what we are used to seeing with our eyes. So when a satellite captures a red, green, and blue band of visible light, then those 3 bands are displayed with their respective colors. And so, yeah, in practice, this essentially means these images are intuitive for us to interpret. Trees will usually be green, dirt will be brown, etc. And these types of imagery are really useful for looking for all sorts of things, including changes in water levels, forest clearings, new trails or paths, new construction, etc. And even just in this example here we have from Lens, we're looking at a 2014 image and a 2020 image to see what changes have happened over a number of years on this property. We see we have some revegetation in this southwest area, and we also have this new solar farm pop up in that time period. So it goes from pretty bare field, and then we can see these solar panels. So just some examples. True color is often sort of the first pass that people will use when looking at a property, just to get a sense of what's going on. And it is really valuable. You can easily identify some changes that way. So when we're thinking about true color imagery or any type of remotely sensed data, what are some tips for interpreting those images? And also, what do we want to consider when we're selecting our imagery? So, like above all else here, note that becoming better at interpreting remotely sensed imagery takes practice. If it's like your first time looking at satellite imagery, you might not be able to quite as confidently identify things as someone who's been doing this for a long time. So practice definitely helps you get better at picking things out and having more confidence in identifying land cover or phenomenon on the ground. But I think these sort of 8 elements can be really useful for keeping in mind as you're looking at satellite imagery. Some of them are pretty intuitive, some a little bit less so. And of course, these all work together. So you're not usually really isolating them one by one, but they can be a useful kind of checklist to go through in your mind. So of course, size is really helpful when we're looking at an image. The size of features can first off help us know kind of what scale we're looking at, but looking at the relative size of features can also provide clues about what those features might be. For example, if you see a thin path on your image, you might not be able to tell if that's a road or a trail. But if you have 2 paths and one is much wider and one is much thinner, then you might be able to conclude that the thinner one is a trail and the wider one is a road. Shape is also really helpful, can be pretty intuitive, but one good key thing to look for here is if you're seeing really geometric shapes, that probably indicates that we're looking at human-made features, and less, geometric, less square shapes will probably indicate more natural features. Of course, this isn't always the case, but if we see like a very square pond, we can probably guess that that is a catchment pond or a reservoir, and probably not natural. Shadows, often these are considered a nuisance in remote sensing because if you have really extreme shadows, it's putting a dark area on the ground where you might be wanting to look at things. But these also can be really useful if you're looking at buildings or different vegetation. The difference in shadow length can really give us useful information about the height of those objects. Color, of course, pretty intuitive, but different colors can indicate different features. It can be helpful to really pay close attention to the hue and the shade. If we're looking at a forest, we might be able to tell we have a lighter green patch here and then a darker green patch here, which might indicate that we're moving from one stand of trees to another. Texture, we don't often think about images as having texture necessarily, but if you look at an image, you might say this one looks a lot smoother, or this area looks smoother, and this area looks a lot rougher, coarser. And a great example of this is with vegetation. If we have a grassy area, that texture, it'll be a lot smoother. And then shrubs will be kind of medium coarseness, and then trees the most coarse. Pattern, if we have repetitive features, that can indicate something about land cover in that location, particularly for human-made features, but for natural ones as well. Association, I think this one is really helpful to keep in mind. Certain things are likely to go together. If we see a playground and a building right next to it, we can probably assume that building is a daycare or an elementary school. If we see agricultural fields and a structure in the middle, we can probably assume that structure is a barn or maybe a farmhouse. So thinking about what things are likely to go together can really help us figure out what we're looking at. Similarly, context. This is maybe the most important element to think about here. It's really hard if you're looking at a satellite image with no context to really know what you're looking at. So this is where it's really important for knowing sort of your property or what you're looking at, thinking about what ecosystem am I looking at? Do I know some history of what's happened on this property in the last few years? And in Lens, we can bring in overlays. We can also use base maps to get some of this. I also often just take the coordinates of what I'm looking at and hop into Google Maps for a second. I was recently looking at a space where there's a structure and some dirt piles around it. And I wasn't sure if that was construction, but double checking on Google Maps, I found out that that was a landscape supply company. So that helped me confirm it wasn't construction and those piles were permanent as like mulch piles that they were selling. So context is really important. Don't be afraid to use any information available to you to get a little more confident about what you're looking at. Okay, and so besides just interpreting data, we want to make sure we're sort of picking the right imagery, the right data to be looking at. So spatial resolution is often the first thing we want to consider here. In Lens, we have imagery ranging from 0.3 meters to over 10 meters. What this resolution means is that 1 pixel in that image is that resolution width and height. So for 0.3 meter, 1 pixel or 1 cell of that image is 30 centimeters by 37 centimeters. And in 10 meter imagery, then 1 cell is 10 meters by 10 meters. And you can see here, if we're working at a pretty big scale, we're looking at a whole property, a whole forest maybe, this lower spatial resolution is pretty sufficient. Like at this zoomed out level, you really can't tell much of a difference between the 1.5 meter and the 30 centimeter. So that's where it often is good to take a first pass at with this higher resolution. It's also often either free or cheaper than the much higher spatial resolution. But this can be really useful for getting that first pass and saying, oh, I've noticed something going on in this specific spot of the property, and now I want to zoom in and look at that more closely. And here's where you can see this lower spatial resolution starts to have some limitations. It's really hard to even make out this building. It just kind of is like a white blob here. Whereas with this sub-meter resolution, you can really clearly see the edges of the building. So if you're looking at smaller scale changes like new construction or a new trail in a park, that's when you probably want to have that higher resolution to be able to see things more clearly. Some other key considerations when you're selecting images, timing, of course, is really important. Like I mentioned, shadows are sometimes useful, but sometimes a nuisance. So depending on whether you want shadows or how extreme you want those shadows to be, make sure you're checking out the time of day and the time of year. Of course, if you're in the north in the winter time, shadows will be a lot more extreme versus like middle of the day in summer. Also, if you have deciduous trees on the land you're wanting to look at, think about whether or not you're more interested in how are the trees doing. I want to look at the trees versus I want to be able to see the ground beneath the trees a little better, and I want to look at the trails running through this property. So whether or not you want to look at the trees with their leaves on or not, you want to think about picking late fall imagery or maybe summertime imagery. Also, if you're in a place where it snows, usually people will want to avoid snow since it kind of covers what's going on the ground. So often people want to avoid those deep winter months or just sort of preview, make sure you check the imagery before ordering it or even loading it in just to make sure you're not looking at that snowy imagery. So we've talked about spectral resolution and spatial resolution. We also have temporal resolution. So hopping back to this slide here, USDA NAEP and Sentinel-2 here are both in Lens for free. And those two have this kind of classic trade-off of high spatial resolution means lower temporal resolution and vice versa. So this 1 meter is higher spatial resolution, but this imagery only comes in every couple of years. So we aren't getting it all that frequently. The temporal resolution is pretty low. Whereas Sentinel-2, we have lower spatial resolution. It's more coarse and grainy here, but this imagery is coming in about every 5 days. So really high temporal resolution. So there's some trade-offs here, and often you'll want to use both types of data. You'll want to use that high spatial resolution to really crisply be able to see what change happened on this land or what is going on here. But if there is a change, you identify something that happened between those couple of years, you can then turn to the Sentinel-2 imagery and really be able to hone in on exactly when did that change happen. And you can, because that comes in about every 5 days, you can get really close to when that happened, probably within about a week or so. And then the last consideration here is clouds. Clouds are often something we have to deal with in remote sensing. Of course, they are between satellites and the Earth. So just always be mindful that clouds and haze might show up in imagery. And if you're ordering imagery through Lens, you want to just double check those previews and make sure that that image is cloud-free. So moving on to a couple other types of remote sensing data, next we're going to talk about false color imagery. So false color imagery, as opposed to true color imagery, where the bands are visualized in their respective colors, false color imagery, they are not. And that's because we are bringing in infrared bands. So this type of data is also often referred to as color infrared. So we are displaying near infrared or shortwave infrared, as well as usually some visible light bands, but then we're not displaying them necessarily in their intuitive respective colors. So these won't be as intuitive to interpret, especially at first, as true color imagery. Like vegetation might not appear green in these images, but because we're bringing in a band or more from the near infrared part of the electromagnetic spectrum, we're able to get additional information that true color wouldn't necessarily provide. So in Lens, we have 3 different types of these false color layers, and we're going to go into each one of them a bit more. So the first one we have displays 3 wavelengths near infrared in red light. It displays the red wavelength, the red band, using green light, and it displays the green band using blue light. You don't really need to remember this, but what is really helpful to remember or refer back to is sort of, what does this actually mean in practice? What can I expect to see when I use this type of data? So healthy vegetation will appear red, and that's because healthy vegetation has high reflectance in the near infrared, meaning that it'll have high values of red light when we display it. Urban areas and exposed ground will be gray or tan, and clear water will be black, or if it's sedimented, it might be a bit blue or cyan. So here are some examples. We have true color on the left and then the false color equivalent on the right. So one thing I think this can be really useful for is getting a high contrast delineation of where do we have water and where do we not. So this example here, we have a flooded river, and in the true color example at first glance, it's even hard to tell, honestly, that there's a river there. The water's so sedimented that it blends in with the bare ground. So it's really hard to tell where the bare ground ends and the water begins. Versus in this false color image, that bare ground is still tan, but that water is that dark blue. So we can really quickly identify the extent of the water. Another common use case for this type of false color imagery is identifying where we have deciduous versus coniferous trees. So in this true color example, pretty much all we can see is just like mottled green. It's really almost impossible to tell where we might have deciduous or coniferous. But deciduous trees have much higher photosynthetic activity, and they are reflecting in the near infrared a lot more. So they show up brighter red, whereas coniferous trees reflect less near infrared, so they show up darker. So we can easily spot out these stands of coniferous trees surrounded by that brighter red of the deciduous trees. So the next type of false color imagery we have, excuse me, displays shortwave infrared using red light. It displays the near infrared band using green light and the green band using blue light. Again, what does this actually mean when we're looking at the imagery? Vegetated areas will be this like really fluorescent green. Water will be black or blue if it's sedimented. Bare earth will be tan and pink. And then what this layer I think is most useful for is looking at recently burned areas, because those areas will be dark red. And even if there's active burning areas or hot areas, those will be like a glowing reddish orange. So here we have a couple examples. On the left here, this was a small fire, and we can see in the true color imagery, we can kind of tell maybe where the fire was. The ground is a lot darker here, but at this edge, it's really hard to tell kind of where the dark from trees ends and the dark from the burn scar begins. Whereas in this false color imagery, it's just so high contrast, it's much easier to see. We have this bright red showing us exactly the perimeter of the fire. And then outside of that, we can see the lighter brown yellow of the grasslands. And then I love this example. I think it's so cool to look at. But in this true color image, we're really just seeing smoke. So we can probably guess there's a wildfire going on, but really hazy, really hard to tell other than that what's going on. In this false color imagery, we can see exactly where there's this glowing, this active burning. And we can even tell, because it's green to the west and reddish to the east here, we can even tell which direction that fire is moving. I see a couple questions coming in. Let me just take a quick pause and read those, make sure I'm not running ahead with some questions. Good question about vegetation and the greater reflectance in the near infrared than the green band. I believe that, yes, healthy vegetation does have a greater reflectance in the near infrared versus the green band. And actually, in a couple more slides, we'll be talking about the vegetation index layer. And that is based largely off of that near infrared because healthy vegetation has such a high reflectance there. So we'll come back to that and then at the end see if that answers your question or not. All right, so the third type of false color imagery we have displays the blue band in red light and then two different shortwave infrared bands using green and blue light. This layer is most often used to differentiate ice and snow from clouds. So ice will be bright red, snow will be red to orange, and then clouds will be white to dark peach. And so again, in this example, in the true color, we can see it's pretty hard to kind of figure out where the clouds end and where the snow might begin. But in this false color image, we have this really high contrast where we have this red showing us ice and snow, and then the white for the clouds. All right, so that wraps up our false color imagery. And then lastly, we're going to talk about index layers. So index layers, indices are really common in remote sensing. These are essentially, we take the different bands that satellite captures and add and subtract them to make an equation that is an approximation for some specific phenomenon on the ground. So we often will have vegetation indices or indices telling us how much moisture is on the ground. One big benefit of these indices is that because they're this calculated number, they are quantifiable, and we can then make a time series analysis of them over time to really gain some deeper insights into how has this land been changing over the past few years. Inlands, we have 4 of these index layers: vegetation, surface moisture, surface water, and snow. Today, we're just going to talk about those first 3. I think these 3 are most often used, and snow follows a pretty similar concept. So if you grasp the first 3, you should be able to explore snow a bit more on your own. So vegetation is based off of the normalized difference vegetation index, often abbreviated to NDVI. So this is calculated using the near infrared band and the red band. So why this equation is the way it is that healthy plants absorb red light and they reflect near infrared. And stress plants will absorb near infrared and reflect more red light, which is why stress plants will often appear more brown or red to us. So these differences will mean that healthy plants will have higher values and stressed plants will have much lower values. So in lens, this will look like healthy, vigorous vegetation will be dark green with values close to 1. and stressed vegetation or no vegetation will be white to yellow to red and have values closer to 0. So here's another example from Lens. We have these 2 time points of the same location, and we can see we're going from really stressed, basically no vegetation, to then some nice dark greens in the second time point here. And with this time series analysis, we can really get a better sense of what's going on here. In a place with seasons, we will pretty much always expect to see some typical seasonal cycles. We'll expect to see higher vegetation values in the summer and then a little bit of a dip in the winter. But here we can see in 2018, this really unexpected seasonal drop, and that is due to a wildfire. And here you can tell where maybe we were looking at 2 true color images from 2017 and 2020. We could tell something maybe happened in between those 2 time points. This time series analysis can really help tell us exactly when that change happened. And then we can also start to see some of that revegetation happening after the fire. So in 2019, kind of a weaker increase in the summer, and then a much higher increase in 2020. One note here with NDVI is that one limitation can be that you can't really differentiate types of vegetation. So we can see here before the fire happened, these peaks were certainly higher than they've been the last few years. So that is a clue that we're not quite back to where we were pre-fire. But we also don't know if this vegetation giving us these green NDVI values in 2020 is trees or grassland. Likely it's not actually trees having regrown after the fire in a couple of years. But that is just one thing to note, is that it's really just a measure for how much photosynthetic activity is happening and not for grasses versus shrubs versus forests. So something to keep in mind when you're using this layer. And then one other thing to note, and this goes for any index layer, also even false color imagery. I think it is helpful just to always kind of look at the index layer or false color imagery and toggle to true color, just to kind of help your brain like wrap itself around what we're actually looking at. But also because of instances like this, in really mountainous areas, shadows can often kind of cause misleading signals. And also maybe similarly in like urban areas, like downtown, if you have skyscrapers and shadows from that, that can kind of throw things. So always double check what you're looking at with true color. And here is just a great example where these shadows from this really mountainous area are kind of inaccurately throwing this, this no vegetation, where there isn't necessarily no vegetation. It's just the darkness from the shadows kind of throwing us here. So surface moisture and surface water, the next 2 index layers, these are both based off of the same index, normalized difference water index, NDWI. And this equation is a similar structure to NDVI, but it uses green and near infrared bands. This is because water reflects, excuse me, more in the green band and absorbs almost all near infrared. So for surface moisture, which is really telling us how saturated is the ground here, values in Lens will range from -0.6 to 0. Low values will be white, indicating dry ground. High values will be blue, indicating saturated ground and water. And again, this one's best used in flat areas or even minimal vegetation. Sometimes in forested areas, even the shadows from trees can make it look like there's water there. But again, really just a reminder to always sort of double check what you're seeing with that true color imagery. And so here's an example. Again, we have 2 time points here in an area where restoration has occurred, and we can see over time this increase in the surface moisture. And we can see these much lighter colors, lower values of surface moisture transitioning to this much darker colors and higher values of surface moisture. And then we have surface water. So again, this is based off of the same index as surface moisture. And this layer is similar, but more useful for kind of telling almost more of a binary of where is there water and where is there not water. So values will range from -0.1 to 0.4, low values indicating dry ground, and high values indicating water. So what this layer can be really useful for is easily looking at the extent of bodies of water. So here, again, we're seeing 2 time points, one from May and one from July. And we can see the extent of this river. In May, we go from much lower water levels to much higher in July. And in this analyzed area where we're looking at year over year, so each of these colored lines represents a different year, we can see that we have these really consistent seasonal patterns. For this river, we can expect in May and September, October, we can expect really low water levels. And then in July, we can expect these much higher water levels. All right, so that wraps up everything for us today. I see I have a few questions I don't think I answered yet, but feel free to keep the questions coming, whether about something here, or I know there's a ton of other concepts in the remote sensing world. We, of course, couldn't cover it all in an hour. So please drop any questions you have in the chat or Q&A. All right. Okay, yes, I see this first question about the resolution and sharpness of that spatial resolution image I was showing. And so sometimes this can be due to if a maybe 50 centimeter image looks a little sharper than a 30 centimeter image. This can be due to a number of factors, from the way that a data provider pan sharpens their image. And it can also be due to if an image was taken maybe on a hazier day, it might just not look quite as crisp as an image taken on a much clearer day. And then for NDVI, distinguishing between deciduous and coniferous vegetation, it is not often as useful for that. And that's where I would say that false color layer is much more of a useful indicator, because that difference is much more isolated to that near infrared band, and NDVI isn't often used to try and identify areas where there are deciduous versus coniferous trees. I would refer to the false color layer. Any other questions?